mic if you get a chance.
Is it working? Okay. So today I'm going to be talking about some work I've done on using deep recurrent neural networks to understand materials in hyperspectral imaging. So before I start, because I know the audience is pretty diverse in nature, I want to introduce the materials that I work on. So I work on this class of materials known as ferroelectrics. So you can think of them as the electrical analog of a magnet. So in this case, you have a material, and it tends to be cubic at a high temperature, but when you cool it below what's known as a Curie temperature, it exhibits a spontaneous polarization that emerges, and you get anomalous effects and dielectric response and the various susceptibilities. And that's caused by a distortion of this B-site cation. So a charged atom actually distorts within the unit cell because of the electronic orbital interactions. Because these materials are ferroelectric and they're essentially the analog of a magnet, if you apply an electric field, they will polarize in one direction, and that remains stable when you release that electric field. And the opposite happens if you apply the opposite bias of electric field, it switches in the other direction. So you have these two different states that these materials can exhibit, and they exhibit a lot of interesting coupled functional properties. One area where it's kind of these materials are important, you can think about these materials as ways to store memory. But the nice thing about ferroelectrics is that they're intrinsically radiation hardened. So they don't have the same problem that you have with magnetic memories, where if radiation comes, you can get a bit flip. And this has led to some pretty sad events, such as the Toyota accelerator incident was attributed back to a single bit flip. So from a material science standpoint, we're interested in understanding these materials, how they switch, and how we can control these states. So these materials exhibit a lot of different crystal structures depending on the chemistry and the material system, and you can drive these materials through different phase transformations using various perturbations. So by applying an electric field, by pushing on the material, applying a force, you can transition between these different states. But understanding and controlling these processes is challenging. But if you could control them, the interfaces between dissimilar regions of crystal structure have very unique and interesting properties that can be used for different devices. So by creating a domain wall, you can create these conductive regions in an insulating material, and that can be used to create a conductive pathway. You can also create really different, interesting, complex switching behaviors that can be used to create beyond binary stability in these systems that you could think about being a beyond binary or neuromorphic logic. So I actually make materials. I'm an experimentalist. So I do a technique called pulse laser deposition, where we grow materials at atomic scale, and this is just some example. And one area that we focus on designing these materials is using strain, so actually pulling on the lattice in different directions to alter how the material breaks down into different structures. And we can do this and create all sorts of different complex structures. And generally, as a design rule, we try to focus on regions where you create competition between different phases, as this allows you to transition between these two by applying some perturbation, so electric field or mechanical force. But as the material starts to get more complicated, there are a range of different interesting coupled reactions that are hard to understand. So to kind of characterize these materials, we relied on this technique called band excitation piezo response force microscopy, built out of Oak Ridge National Lab. This is an atomic force microscopy technique, so you can think of it as taking a nanometer scale probe and physically touching it to your surface. And that allows you to measure the topography of the surface, but also you can use that to perturb the material. So you can use that to apply electric field, to drive transformations, and you can actually measure the response of the material using this technique. So because we have this cantilever, it was really important that we actually use the resonance amplification to actually get a large signal. But as you're scanning your tip across your surface, you're having changing tip contact resonance that causes frequency shifts. So to get the measurement to be appropriately, what we actually do is we apply a band excitation waveform, which has a spectral density across a band of frequencies near the cantilever resonance, and measure the full response. So that's one way that this data dimensionality increases. But then we can also drive this material through transformations using the tip. So a large, lower frequency DC bipolar triangular waveform that we apply that switches the material from up to down poled state. And we can actually measure the piezo response through that transition at every single pixel. So this provides a lot of information about how the material is responding, but it's really difficult to analyze. So we have all of this information that we can extract from fitting that cantilever resonance to the simple harmonic oscillator model. And we know it contains a lot of interesting insight about the physics of the material and how it responds. But we don't have a way to actually extract the actual physics and interpret what it means. And if you look at the different functional forms of these different response curves, there's a lot of interesting subtle features in the response curves that can't be well fit to an empirical model. So I thought about how I could go about applying machine learning to this problem. So one of the key challenges that we have is that the model needs to be generalizable. So it needs to be able to deal with loops that have this very classical-like shape, something that has a concavity, and be able to capture that feature in its embedding. And then in the end, it needs to be interpretable. In the end, I'm a physicist. So I want to have a physical understanding that I can understand once I actually go through and do this. So I thought about training a neural network on this approach to identify different features that we're interested in, using this neural network essentially for spectral unmixing. So trying to identify important features that I could then focus in on, hone in on, and use my physics knowledge to understand what that actually means. So I use this technique called an autoencoder, which has been brought up a lot today. You take an input and it takes all of the information, all the spectra that you have, and it deconstructs it into its most important statistical components. And then by having a low-dimensional embedding layer, you can start to encode some information about or create a low-dimensional representation of this data. And then by optimizing it based on the input signal, training essentially an identity function, you're able to optimize this using kind of conventional approaches. So because this neural network or the data is spectral in nature, so each point depends on the previous point before it, it was important to include that concept into the network structure. So the way I did it, which is common from natural language processing, where the order of the words matter, is to use this concept of recurrence. So this network takes the first time step, passes it through to the neuron, and then the information is passed on recurrently, where information from the previous time step is passed on to the next time step along with the next data point. And this allows you to include the concept of temporal dependence, which is important in this data, something that PCA couldn't do. So in building a neural network, you build a series of different neurons into layers, and then stack those layers deeper through the network, and that allows you to build more complex abstractions of that information. You're kind of breaking it out into the most important statistical components. Because we're using a recurrent network, we can just take that last time step, which encodes information from the previous time steps, and pass it to this low-dimensional embedding layer, where we're actually trying to compress the information into a low-dimensional representation that we can then eventually use. And then if we repeat that back into its original spectral domain, and then go through the decoder, actually to regenerate the original spectra, what you get is you can regenerate the original response, and then you can just optimize the network based on the mean squared error and use common optimization algorithms to optimize it. Because we wanted to include both long and short-term temporal dependencies, we use this neural network architecture called long short-term memory, which is able to include that concept by having a series of gated neurons within the system that controls how much information from the previous time step the neuron forgets, how much it forms a new memory, and then also generates a new memory output, which is passed on, that allows you to have both short and long-term temporal information included. So if you do this, and these are the static images which were of the actual structure, which was taken before and after this event, and you train this autoencoder and then output that low-dimensional representation, we didn't provide it with any of the pixel positions. So if we reconstruct these maps of just analyzing the spectra, and the maps reflect the original structure that we know that exists in the material, we, as a first pass, have a validation that we're actually learning something interesting. The problem with analyzing these maps is that they're all competing against one another. So it's very hard to isolate out what's interesting and how to understand this. What we really want is we want maps that look like this, where you have one type of structure showing a large response, and then the rest being essentially zero. So we can think about how we can change how the network is is training to encourage this so we can encourage sparsity by enforcing sparsity. So instead of just training the loss function on the mean squared error, we can add L1 normalization, which is just a penalty on the weights of, of the low-dimensional embedding layer. And if we look at how this would look, if we have the mean squared error and it propagates out from this point, it tends to intersect at values where some of the weights are non-zero, but most of the weights are 0. So this is a way to encode sparsity into that low-dimensional embedding layer, and then when we train that network, we get these maps that are much easier to interpret. So we're seeing one type of response in each of these maps. We can then go in and try to figure out what they mean. So now that we have this network that's fully trained, we can also play with how we actually visualize what's going on. So instead of using this network as just a autoencoder, we can use it as a generator where we tune the input. So what we can do is we can go in and we can slowly turn this like a knob and see how, as we change, so this color reflects the color in this map. So this is a very classical response of what's known as a C-like domain, where we can turn that knob, see how that embedding affects the feature and understand it from a physical perspective. We can also look at some more complex things, like seeing a gradient from this left-hand boundary to the right-hand boundary, and how you have the emergence of this intermediate concavity, which is related to the physics of the switching mechanism. So this allowed us to identify this interesting feature, and then we could go back to our actual raw data and figure out with our physical understanding what this actually meant. So if we were to look at this switching event, this intermediate concavity was associated with an elastic hardening step, which indicated a transition from down-poled to in-plane poled to then, or in this case, up-poled to in-plane poled to down-poled, which is very different than the classical ferroelectric switching mechanism. So this allowed us to identify and understand the spatial distributions of these interesting switching mechanisms. I also went on to train this on a more complicated data structure. So this is the resonance response curve, which has a complexity in terms of its functional form that's too complex to even try to analyze using basic empirical models. And again, you can see immediately all the important features related to the domain, to the different structure. And again, the generator showed interesting things that were related back to the physics, like gradients in the degree of response that's related to elastic hardening that we could then back calculate out to relate back to the geometry of the material. And in doing this, we can build these simple models once we identify these important features and use our physical understanding and actually determine something new that we could have, had we had known that this was an important feature to focus on, identified. But here we were able to immediately use this technique coupled with the machine learning to immediately identify that this is important, and then we could focus our effort and understand it from a physical standpoint. So with that, I'm gonna, because I'm running out of time, I'm gonna skip through some of the stuff. But what this really allowed us to do is that we take this data, which is commonly acquired in material sciences, hyperspectral images, and use machine learning to really help us identify important features that we could then hone in on and focus on. So here you can see gradients in the relative ferroelastic character, which is related to its energy conversion potential. So these are really important things for material scientists to be able to identify quickly, and this technique allows it. And even we could show things like the quality factor. So at that boundary, we could then look at other channels and signals of response and see that the material was actually absorbing all of the input energy that we were putting into it, which means it shows increased electromechanical energy harvesting. And then we could use this as a design rule to go back when we try to make the materials to create materials that have even better properties. So this is not just limited to this one technique. This is an electron microscope, and there's a technique called energy loss spectroscopy, which looks at the change in the binding of these atoms and the electronic energy states. And this collects a very similar type of data where you send an electron through the material, and you're measuring the amount of energy that electron loses. And you can train the autoencoder. This is just a little test example on this data set. So these are actually individual atoms that we're imaging right here. But what's really interesting is that this is an interface between two dissimilar materials, and you're able to see the change in the charge density electronic orbitals and their spatial distribution related to that. And then again, you can use the autoencoder as a generator and correlate that back to changes in the peak shifts and the magnitude of the peak shifts, and allows you to identify really quickly. So with that, thank you. The code for all of the autoencoder analysis and also my data is provided on that QR code link. Thank you.